record? Or... Okay.
Yes.
Perfect. Okay. Well, welcome to the second talk in our seminar today. Well, I am Eduardo Serpa, and I have the pleasure of introducing our next speaker. She is Mariel Saez from Universidad Católica de Chile. Well, Mariel, she got her PhD from Stanford University under the supervision of Raf Maceo. Then she held a postdoctoral position in Germany at Max Planck Institute. Okay, she is currently associate professor at the Faculty of Mathematics at UC Chile. Her research interests are in geometric analysis, in particular in geometric flows, minimal surfaces, and fractional equation arising from geometry. She has held visiting position in many universities around the world, as Montreal, Berkeley, London, Berlin, Madrid, among others. She currently is the representative of Latin America at the Committee for Developing Countries at the National Mathematical Union. Thank you, Mariel, for doing that important task for our community. For today, the title of the talk, we can see it on the screen, is the k-Yamabe flow and its solitons. So, Mariel, please go ahead.
Well, thank you very much for the invitation. And yeah, today I'm going to talk about the k-Yamabe problem. So I know that this is an analysis audience, so I'm going to try to introduce the geometric question, but soon I'm going to go more to the analytic part and the analytic difficulties of the question. And I'm going to show a result and a problem that we're starting to study. So it's kind of the simplest case, and there's still many things that are unknown to us. So let me start with the Yamabe problem that is, and this is not moving, I see. Oh, there's some issue with the connection, I think, because the screen is not moving.
No, it's not moving. We can see your mouse moving out.
Oh, that's weird. Okay, let me try. No. Why is it not moving? Oh, never had so many issues with Zoom. Okay, let me try to do this again. Okay, there we go.
Yeah.
So, okay, so the classical Yamabe problem, what it tries to do is, given a Riemannian manifold that in the simplest case is compact manifold without boundary, so you can think that in the easier case, and a metric. This is a Riemannian metric, unlike the metrics that we were seeing before. So this is something that has positive signature, positive definite. The question is, can we find a conformal metric that means a multiple of the metric, like the one that I'm showing here? I don't know if this is working. Such that the new metric has constant scalar curvature. Okay, so this is a question in geometry, but has an analytic counterpart. And let's see if now this moves. I think it's not moving again. I'm not sure why. Okay, it doesn't work somehow. Okay, let me try to share. Let me try to do this from the iPad. I think it's gonna work better, it seems. Hold on. Okay, where's Zoom here? Oh. Okay, I don't know if you can see now the screen. Can you see the screen?
Yes, it's okay.
Okay, now it's fine. So, okay, let me go again. So we were trying to find metrics with constant scalar curvature that has this shape, and that's equivalent to solve a PDE, an elliptic PDE, that is the one here. And well, so like the question basically is, can we find a solution to that PDE? And that PDE doesn't look too bad, it's elliptic, and actually has a variational structure, so it looks like it's something that we should be able to solve. It's actually, if you want to write an energy for that, the energy for that is something that looks like gradient plus the original scalar curvature, and this is, I guess, the important part. And you get something here like v to the n plus 2, n minus 2 plus 1. And it turns out that this is actually, from the analytic point of view, quite a hard problem, because if you want to use kind of standard PDE theory, this last term that you're seeing here, is critical in terms of Sobolev embedding. So it turns out that if you have something like an energy bound, that's not enough to have convergence in a weak sense if you want to use kind of a variational method or things like that, and that has inspired a lot of analysis actually. So there are many people that have studied the equation just from the point of view of the equation, but in geometry, I mean, the motivation, the original motivation is this Yamabe problem, and there's one more restriction that I actually didn't write here, that is that the function actually should be positive, because we want this to represent a Riemann matrix. So it's important for this to be actually strictly positive. So what are the motivations for this question? Let me tell you what are the answers that we know for these questions also. So the main motivation at the time, this was originally posed by Yamabe in the 60s. So what he had in mind was the geometrization conjecture. And in dimension 2, we have the uniformization theorem that relates geometry and topology. So in dimension 2, we have the Gauss-Bonnet formula. The Gauss-Bonnet formula that says that the Euler characteristic, and I'm gonna miss a number here, so I had written it here somewhere, is 2 pi times the Euler characteristic is the integral of the scalar, the Gaussian curvature over this. So what Yamabe was thinking, okay, so in 2 dimensions, if we find a constant Gaussian curvature, then that's directly related to topology, and maybe an objects with constant curvature are easier to classify. So maybe if we can impose some curvature condition that we can solve, then we can say something about topology. So the question was originally more inspired from topology, but at the end, it turned out that actually there was more motivation from analysis to actually study this question. And let me tell you what the history of the problem is. So in the 60s, as I said, Yamabe posed the problem, and actually he claimed a solution. He claimed that he knew how to do it, but he didn't know how to answer the topological question. 8 years later, Schrödinger was studying this solution, and he found actually a mistake in Yamabe's solution. So he found a mistake, and actually was due to this critical Sobolev embedding and the method that he had used to solve. So he found a mistake, and he could solve it only in some cases. He could solve it under an additional condition, and he gave a partial solution. And the partial solution actually was related to the sphere. Actually, he could solve this in the cases that something that is called the Yamabe invariant, it was strictly bounded by some constant that he didn't know what the constant was, but it's sort of something that you can think about as an eigenvalue problem. So he had something that would be kind of a bound for the first eigenvalue, and under that condition, he could say that there was a solution. So that was his contribution. And then Obam sort of improved a little bit Schrödinger's problem, and he could say that, okay, this solution works up to a certain number that is related to the sphere, and this is basically he improved basically Schrödinger's result, proved, and this work when the manifold is not locally conformally flat. It's not locally conformally flat. I'm gonna say in a minute what that means. And in 84, finally, Rick Shane completed the solution and he treated the locally conformally flat case. That is basically when you're conformal to the sphere. The difficult case in this situation was actually things that are conformal to a sphere or to Rn, because in the sphere in particular, you have many solutions. So somehow you have to deal with the fact that you have a very non-unique solution. And this was kind of the very difficult case. This is actually a complete solution only in the closed case. You have still questions that are not fully understood. For instance, in the non-compact case, it's known not to be true always. There are examples in which this is not true. And there are partial results on cases that is true, but it's not known exactly when it's true and when it's not true. So there are partial results here. It's not completely unknown, but it's true that it's known that it's not always true, and it's known that in some cases it is true. In the case of manifolds with boundary, you have to modify a little bit the question, and many people know this case as the Escobar problem, that you need to prescribe something at the boundary as well. And there are many partial results, but again, it's not completely understood. So there are still things that need to be done even for the classical Yamabe problem. Okay, so, but today I want to, as in the title, I said I want to talk about a modification of the Yamabe problem. And I had the word flow in my title, so let me talk a little bit about the Yamabe flow, and then I'll go to my flow. So the Yamabe flow was a method that was proposed by Hamilton after the Yamabe problem was already solved, but he somehow at the time was kind of introducing the Ricci flow, and the question was more or less, I mean, can we solve the Yamabe problem maybe in an easier way if we use a geometric flow? And he proposed this Yamabe flow, and the idea was basically you wanted to now let the metric evolve with a speed that was the scalar curvature. But he also asked for the metric to be conformal. By this, I mean the derivative in time. So sorry, let me write it like this to be more clear, I guess. G is conformal for every time. So this is for every time. So if you look at the equation that I wrote, the elliptic equation that I wrote a few slides above, this one basically would be the parabolic analog to this equation. So you would have Vt equal to Laplacian V minus R minus this term here, and you would be trying to solve that parabolic equation. And let me go back to the Yamabe flow. And well, that was his proposal. So the advantage of geometric flows are that while they exist, they're very regular, but as we saw in the talk before, you may have that singularities develop in finite time. And in that case, you need to be able to analyze singularities. So it's more regular in some sense, and you have other issues basically that you see in other things. So this problem in the context of the case before was studied in 1994, I think, by Ye, that showed that this worked in the difficult case. So in the worked well, if M is locally conformally flat. That was kind of the difficult case before, the one that M is locally conformal to a sphere. But for the general case, this turned out to be much more difficult. And actually, many, many years later, Simon Brendle found a solution in the other cases. So the other cases, I think 2007, so like 20 years later. So it turned out that somehow the Yamabe flow was more difficult in the cases that the other approach was easier, and easier in the difficult case. But still, there are many people working, as I said, in the other cases, in the cases that are not even known in the elliptic case, like the non-compact one, or in the case with boundary, actually, there are not so many things for the flow. But for at least for the non-compact case, there are many people that have tried to work on this Yamabe flow, and they're only partial results as well. Okay, so as I said, the original motivation for this question was topological, and I haven't said much about that part in the problem before. And it turns out that actually having constant scalar curvature is something that is weak enough that you can solve, but not strong enough that you can classify in general. So for the original problem, at least, of trying to classify, that was solved now by Ricci flow. Actually, the geometrization conjecture was solved by Ricci flow and not the Yamabe flow. It was not good enough. So I guess the remaining question is, can we pose another question that may be better suited to related with topology? And again, inspired by the uniformization theorem, I'm gonna say that there's a Gauss-Bonnet formula, the Chern-Gauss-Bonnet formula for manifolds that are even dimensional, so 4, 6, 8, etc. And the question is, can we maybe use that information to try to create a new flow that give us more, or a new equation that give us more information about topology? The Gauss-Bonnet formula in general is kind of something that is not very nice to write, so that's why I wrote it for n equal 4, because with this one, I guess I can explain why I'm gonna choose what I'm choosing. In n equal 4, again, you have like this quantity that is a conformal invariant, something that is a topological invariant, something that doesn't change when you do conformal changes of the metric, or actually doesn't depend on geometry, that only depends on topology. This quantity is something that we call the Weil tensor, and is something that scales well with conformal changes. So actually, this quantity, scales exactly opposite to the measure on the manifold. So this quantity is also conformal invariant. So all the conformal information somehow should be hidden here, but because these two things do not depend on conformal changes, this integral also doesn't depend on conformal changes. And all these things are things, all this side is a side that depends on geometry, actually. So the question is, can we pose somehow a geometric question that we can turn into an analytic one that tells us more information about some of these parts being constant? And what I'm gonna try to do is actually pose a geometric flow that involves quantities that are related to this curvature here. So I'm gonna focus on trying to explain what this curvature is. Okay, so the Riemannian tensor, the Riemannian curvature, this is what I'm gonna say is not precise, but the metric is in coordinates given by a matrix of two entries, right? It's just a matrix. It's a two tensor. It's Gij, and the Riemannian tensor is something that is like second derivatives of this Riemannian matrix. It has more components, but basically you can think about it something that considers terms of the form that are two derivatives. So I'm gonna take derivatives with respect to things and things like that. It has also first derivatives and other things. I mean, it's a bit more complicated than that, but it's something that depends on 4 indices. It's a 4 tensor. And that object that has all the information about second derivatives of the metric, you can decompose into this part that is the Weil tensor. That is something that, as I said, we know exactly how it behaves when we do conformal changes of metric. And this part, this is just a metric, so we also know how that changes when we scale it. And this part here is what is usually known as the Schouten tensor. So this is called usually the Schouten tensor. And this is the one that is actually encoding all the information that we want to have about conformal changes of metrics. So basically, if we want to prescribe something to be constant, it would be good to do something that is sort of involving this Schouten tensor. And actually what you see inside my integral here is exactly the Schouten tensor scaled by the inverse of the metric, and that is because you want things to be invariant when you do change of coordinates. So I mean, this is kind of the natural geometric quantity. Okay, so this is a 2 tensor. It's something that's a matrix that has 2 indices if you want to represent it in coordinates, and it's a tensor that is positive actually. So it's something that has eigenvalues. It's symmetric and it's not positive. It's symmetric, and then you can have n eigenvalues, and these sigma curvatures actually are related to the eigenvalues. And let me explain it in a minute. What I mean by the sigma 2. So here I have how this scales under conformal changes. So if you take the metric in this form, then what you're gonna see as your new Schouten tensor is gonna look like that. And sigma 2, actually what it's doing is taking the eigenvalues of this matrix and taking all the sums of eigenvalues of this form. And here the lambdas are the eigenvalues of AGW. And in general, if you want to do this more generally, you have, this is an n by n matrix, so you have n eigenvalues, so you have things that look like this. Okay, so in general, sigma k is gonna be that. Depending on the literature that you look at, this could be this could have some constant of normalization, because actually these are very natural quantities in terms of matrices. You don't really need to know exactly what the eigenvalues are to compute these quantities. And sorry, I want to check how I'm doing with time. So basically, this is what appears when you compute the characteristic polynomial. So if you can compute the determinant of G minus 1 AG minus the identity, what you're gonna see exactly, well, is something, is a polynomial, minus lambda. You're gonna see something that is like lambda to the n plus an minus 1, lambda to the n minus 1, etc., plus a0. And this is actually sigma 1. This is sigma 1. This coefficient here is gonna be, this is sigma 1, sigma 2, and sigma n. So actually, these are quantities that you can compute in terms of determinants. So it's something that you know what it is, and you can compute an equation in terms of this horrible quantity that you see here. Okay, so the k-Yamabe problem that it was in my title is basically the question: can you find a metric that has constant sigma k curvature? And the goal would be in an even dimensional manifold to find it in the case that k is exactly half the dimension, because this would be kind of the conformal one. But since we're posing it for sigma k, we can do it for any k. I mean, we can ask the question for any k. Okay, so here I'm showing what the analytic question is sigma k of that. So you more or less would have to look at the eigenvalues of that and do multiplications of that and try to find some w that makes that constant. The problem is fully nonlinear, so it's kind of hard to treat and has several issues. The regularity theory for fully nonlinear equations is more difficult than for quasi-linear equations or linear equations, of course. And there are some issues even with ellipticity in this problem here. So first thing is that you need more regularity estimates to be working with this, and for that you actually need to restrict the class of functions that you can work with. So one very classical way of making this equation an elliptic equation, because it's not in general an elliptic equation if you do this in general, is to ask for solutions that are in the positive cone. or in some cones. So what is the positive cone? That will be the matrix G, such that all the sigmas up to K are positive. Okay, and if you restrict to metrics where that are in this cone, for instance, then you know that your problem is elliptic. But if you don't put any condition, then you cannot really use PDE theory. So, or at least it's not so easy to use PDE theory because the problem is not even elliptic. This is not the only condition that you can pose for ellipticity, but yeah, I mean, there are a few other cases that are kind of have been studied, but there are always some sort of restriction. And as I said, I'm interested in the flow approach. So I'm interested in this geometric problem. Again, here I mean the derivative. And again, I'm looking at conformal metrics. So I'm thinking that G at a time t is something that looks like, and here there are different choices of how you write the conformal factor, but it's some function here that is positive. So if just to be consistent with what I had before, where this depends on t and the background metric is fixed. So it's gonna be a partial differential equation for this conformal factor w, and soon we're gonna rewrite this in a different way because it's gonna be more convenient. So one question is also what is the best way of writing the conformal factor, but I'm gonna say something. Okay, so we want to look at solutions of this geometric flow. As I said, it's quite nonlinear and it's hard to treat. Still, some people have looked at similar geometric flows. So similar geometric flows were treated by one-on-one in the locally conformally flat case when n was not equal to 2k, so actually not in the conformal dimension, and they were looking again at things that were closed, so compact and with no boundary. In our case, we were more interested in the non-compact case because also this would apply maybe to the Yamabe flow, but of course this is difficult in general, so we decided to start by looking at simpler solutions, and that would be at soliton type solutions, at self-similar solutions. And these are solutions that are basically have a very special shape. That is this one that I tried to write here. So basically they're just a function of t, and the second term here would be just, you can think about basically as a time-dependent reparametrization of the original metric. So the idea, a bit of what we saw also in the previous talk, would be to look at the simpler solution because these probably are the right models for certain singularities. So that was our starting point, and the equation in this case becomes a little bit simpler. That would be something like this. So it's something that's now, again, an elliptic equation. This is the lead derivative of that. Don't worry too much about that because I'm gonna also get rid of that in a minute. And we're gonna look at soliton solutions that this x here actually is not gonna be, in general, it's a general vector field, but for us, x is gonna be the gradient of some function phi that we need to find. It's part of the things that we need to find a soliton. What is the correct phi? So when you have that composition, that x is the gradient of something, then G0 is called a gradient soliton. So we're gonna look at gradient solitons. Okay, so why are we looking at this? In the classical case, in the case k equal 1, this problem was studied by, Okay, this problem was studied by Sessum and Daskalopoulos. And they showed actually that if you impose some curvature condition on your background metric, then all solutions are rotationally symmetric. So again, you go from a PDE that is fully linear to an ODE. So again, you simplify a bit more the problem. We said, okay, maybe we can look then at rotationally symmetric solutions. And the problem then it would be a bit simpler. And in fact, you can show that even in this case, and this was actually shown not by us, but was shown by Catino, Mantegazza, and Massieri, that if you impose curvature conditions, Massieri, curvature conditions on G0, then solutions are rotationally symmetric. Rotationally symmetric. And in the rotationally symmetric case, as I said, in the case k = 1, Natasha Sessum and Toti Daskalopoulos showed that, did a complete classification of those solutions. So the question is, okay, can we do this for general K, and what can we say about that, given that we have a more nonlinear problem and more restrictions on what can be a solution, actually, what is kind of an admissible solution. Okay, so in the case K = 1, the problem that they studied, the Yamabe problem in their case, they wrote, as I said, you have choices of how you write your conformal factor. They wrote it in this way, and they show that if you write your conformal factor in that way, then that you should satisfy an equation of this form, the one that I wrote here. And this type of problem, this kind of fast diffusion problems, are problems that have been very, very well studied in the case of Laplacian. So basically what they did is they used lots of results that were existing in this case. They improved them in some cases, and they interpreted this in terms of the Yamabe problem. Again, you have this coefficient appearing here. This number that has to appear somehow because the problem is critical. They put it basically inside the Laplacian. And they have a very nice work showing lots of properties for these solitons. So we said, okay, maybe we can do something similar. And what we did is, okay, let me tell you how are we gonna write the metric. So in our case, we're gonna write again the metric inspired in what they did, and the thing that we're gonna take is 4k n plus 2k times G0 and try to see what is the PDE that you should satisfy. And it turns out that the PDE is not super bad, but it's also not super nice. And it's this PDE here. There is something that you get under the assumption actually that you use rotationally symmetric. So actually, if you use rotationally symmetric, then you can see that it solves this PDE. This is the same thing for k = 1. So basically, we can generalize, and if you write k = 1, the PDE actually agrees with the PDE that they got. The rho here I haven't explained, and I should have. The rho is a quantity that's related to the soliton equation, and this is something that I forgot to say, that I had it here as well. The rho is related to this function tau, because we have different types of solitons, as we have different types of singularities as well. And this is something that I forgot that I had to say, so let me go back and say it. So this rho here is minus tau prime at 0, and basically tells you if the soliton is something that is contracting, is shrinking, expanding, or just a steady soliton. So usually what you can see, what matters about this is the sign of this rho. So let me add it as a remark here. For rho bigger than 0, we say the soliton is shrinking. Actually, you can say exactly what the shape of this tau is. So tau is going to be, in this case, something that looks like t minus t to some power here that I'm gonna be explicit later. If rho is equal to 0, we say the soliton is steady. And actually that function tau is something like looks like e to the minus some number here times t. And in the case that rho is less than 0, the soliton is expanding. It's expanding. And in that case, actually the tau, you can also say exactly how it looks. It's like t to the minus some power. It's not exactly that power, but it's minus some power. I'm gonna be more precise about that. So it's something that is sort of singular in some sense at time 0, but it expands for positive times. Okay, so let me go back to here. So this is because I wanted to discuss the parameters. This parameter, as I say, is related to the soliton equation. This theta is something that I'm gonna have to explain, but we're gonna see that it's something that is gonna have to satisfy this equation, I mean this restriction, and I'm gonna explain in a minute why. And it's something that comes from the fact that this is a gradient soliton. So theta is a parameter related to the soliton being a gradient soliton, being of gradient type. Okay, so we have the question, can we say something about the solutions of the equation? And we can actually, we can say the following. So when we have the following relationship between n and k, so n bigger or equal than to k, we also have the conformal case in this situation. Then we can find radially symmetric solutions if and only if the parameter theta that I mentioned before is positive, and this restriction that we had from before, that I'm gonna explain where these two come from. And if we don't have this restriction, if we don't have that n is bigger than 2k, so if we're in the opposite case, when n is smaller than 2k, then actually solutions are not admissible. So there are things that do go outside the cone. You can start with something that has positive, sigma k, let's say, or the different sigmas, but you cannot have a solution that lies completely in the positive cone. So that means that solutions become not elliptic in some sense. I mean, here they're going to be ODE, so it's something that you could still study, but if you want to use really this for describing singularities, those are not going to be describing any singularity, because in general the flow is going to be studied in the context of these things being elliptic. So I mean, I guess the result is that in that case we do not have admissible solutions if rho is less than 2 theta, but when rho is bigger than 2 theta, we can find solutions. So in the case of rho positive, that means shrinking solitons. And then we can actually describe even how is the behavior at infinity. And here's what M is. And we can do a bit more trying to understand how different are the solutions for the different case, basically. And what we can say is what is the decay rate in each case. And maybe I don't want to describe this in all detail, and I think I lost my track of time, so I should be finishing now. So let me say just one thing. I'm gonna finish here, but all the solutions that we have in the case n is bigger than 2k, the decays are exactly the same as in the case of the classical Yamabe flow, but we have very different behaviors when n is equal to 2k. And the analysis here, we do it in a similar way that it was done for the case k equal to 1, but you need to be a lot more delicate, because the equations become degenerate actually with the k. I mean, the analysis that you want to do, the nonlinear analysis, is actually very degenerate, especially at the origin. And this requires a really very delicate analysis. And I wanted to describe a little bit how the solutions are, but I guess I'm out of time, so I'm going to stop here.
Yeah, you can take a couple of minutes if you want to. It wasn't your fault, so
Well, kind of. It's a little bit my fault. So yeah, I mean, if anyone wants to see something about the solutions, I can tell you something, but maybe it's late, so I don't know. I can also skip.
okay. Well, thank you very much, Mariel, for this talk. Thank you very much. So the mic are open. So if you have questions, just feel free to ask Mariel. Okay. Any questions you have?
Hello, Professor Mariel. Thank you for your talk. I have a question. There is some classification results for solitons of this flow in low dimensions, for example, two-dimensional and three-dimensional.
Yes. I don't know actually, because okay, in 2 dimensions you can only, I mean, 2 dimensions basically is the same as a Yamabe flow, right? You don't have, or I mean, it's the same as prescribing scalar curvature, I guess. So you need at least 3 dimensions for this to make sense. And I guess most of the work actually has been done from dimension 4 and higher, because I guess this starts being interesting when n is equal to 4 and when you have sigma 2 related to sigma 4. And in that case, there are many things actually when you study sigma 2 and n equal to 4. But then for higher dimensions, I think there are not so many results actually, especially when n is equal to 2k.
Okay, thanks.
Think if there are any other questions, please.
Let me maybe turn this off.
Yeah, I was on your slides. Well, Maria, I have a question. So for when you look for the soliton, what is the speed of it? In fact, the speed of the soliton you are looking for. We can hear you. You're mute. You're mute.
I am mute. Okay. Yeah, the speed of the equation in our setting is sigma k to the 1 over k. The 1 over k is a bit of an artificial thing. We put it because we don't have to carry around so many k's when we take derivatives, actually. This is a homogeneity 1, otherwise it's homogeneity k. That's the only reason. And because you have this restriction of sigma k being positive, is something that you can do. It's not a problem doing that. Okay, so in that sense, the speed of the equation is sigma k of the Schouten tensor.
Okay.
I don't know if that answers the question.
And if you were looking for a solution in order to give an answer to your original problem, right? So
Right.
From the fact that your solution is indeed a soliton, you get more information or something more about your original problem, or?
Well, that's actually one of the things that we want to do now is to see if there are situations where this actually in some sense you want solitons to show that this doesn't happen, right? I mean, to show that if you have a singularity, then it should be one of these solitons, but you want to find some reason why this cannot happen. Okay, so for instance, when n is less than 2k, this already tells you that you cannot have solitons that are steady or expanding, that all of them are shrinking, and this should be easier to classify. Okay, so yeah, you need a little bit more to be able to say something about the original problem, but this already tells you that probably in the case n smaller than 2k and in the positive cone, you're not gonna have singularities if you run the flow, if you run the original flow. But
Nice.
yeah, I mean, this is something to do still. And then you have, of course, the cases that sigma k is not positive, I guess, that they're still interesting.
Thank you. Any other question to the audience? Okay. If not, well, we